Let's suppose that I've got this little environment here, and let's suppose that this environment, this little rectangle, is kept at a constant temperature. Okay, I guess I'll call that T sub R for room temperature. Okay, and then let's suppose that we have this thing, and it is a certain temperature above room temperature, and we take this thing and move it into this environment. And we're going to assume that this environment is kept at a steady temperature. In other words, moving this thing in there doesn't change the temperature of its surroundings at all. So this has an initial temperature. Now, if you think about it, this thing is not, it's going to begin cooling. In other words, when we move this into the room temperature, take it away from the heat source or whatever, it's going to start decreasing toward room temperature. And the thing is, think about it, if this was well above room temperature, it would start cooling very fast to room temperature. Imagine that you have a pan of boiling water on the stove. And let's suppose it's the surrounding temperature is very cold. As soon as you take that pan of boiling water off the stove, it starts cooling very quickly. But, it'll stop boiling almost immediately. But imagine that the temperature on the stove, of the water on the stove, is very close to the surrounding temperature. Well, when you take it off of the stove, it will start cooling toward room temperature, but at a much slower rate. So let's see if we can think about what this might look like graphically. If I have an axis for temperature and an axis for time here. So here we have the axis for time, and up here we have the axis for temperature, uppercase T. And let's put in room temperature. Let's suppose this right here is room temperature. Well, what happens is when you first remove the object from the stove, it's going to start cooling very quickly. But as it gets toward room temperature, it kind of levels off and becomes asymptotic to the room temperature. In other words, what we could say is, well, the rate at which this temperature changes over time is proportional to the change in the temperature and the room temperature. In other words, the surrounding temperature. That's what we could say. And that makes sense. Well, this statement here is Newton's law of cooling. This is Newton's law of cooling. And it says the rate of change in the temperature is directly proportional to the difference between the temperature and its surrounding temperature, the temperature of the object and its surrounding temperature. So we can get an idea about, what the temperature is for any given time if we can solve this differential equation. It's a differential equation. And what we want to do, though, is we want to put this in differential form. In other words, this is what we call a separable differential equation. So what we want to do to begin solving this is put it in differential form. So we have dt over t minus tr equals k dt. Now, in separating variables in a differential equation like this, you can think of this d big T over d little t as like a fraction. Just think of it as a fraction. And think about, can I get the big T over here with the big T and the dt over here by just using multiplication or division? In other words, it's like I'm dividing both sides by T minus big TR. It's like I'm dividing both sides by that and then multiplying both sides by dt. If you can do that and get the big T's on one side and the little, this little t on the other side with everything else, then that's a separable differential equation. And what we need is now to find out what t is, big T. So this is set up so that we can integrate it. So if you notice, I can set up an integral. So on the one side I've got big T over T minus TR. And on the other side I've got the integral of K dt. Like that. So what I need to do is solve this now, or integrate both sides. Now notice that this over here, T sub r, that's just a constant. This is the surrounding temperature. And T is my variable. So on this side over here, I'm just going to put log of T minus TR. Like that. And you might wonder, well, why didn't you put an absolute value? Well, in this example here, we're saying that T is well, the temperature is above the room temperature. In other words, it's cooling. So T minus T sub r is going to be positive. So I don't have to worry about the absolute value. Now over here, let me integrate this. This is going to be KT because K is just a constant plus C. There we have it. Now remember, I'm trying to solve for T here, big T. So the next thing I might want to do is apply E to both sides. In other words, I'm going to get rid of that log, and now I have T minus TR equals E to the KT plus C. See? I just applied E to both sides. Now when I do that, notice I've got T minus TR equals, and let me do this, let me make a change. I'm going to rewrite this part over here, the exponent part right here, as E to the C, E to the KT. And it's okay to do that because, a property of exponents. See, I just wrote it this way. And then when I do that, let me just do this. Let me say this is T minus TR and equals, and I'm just going to change this E to the C. That's just a constant, right? E to the C is just a constant. It's kind of a messy looking constant, E to some power. So let me just write that as, C1 maybe. There's what I have. Okay. So I just wrote it that way. And now I've solved that differential equation. Notice I've got, and I could go ahead and say, well, T is equal to T sub R, just add that to both sides, plus C1 E to the KT. Now, to solve a differential, so this is my solution. So you give me a room temperature I can put in for TR, and notice I've still got two things to solve for. I still have to find this constant right here, C1, and I still have to find K. The way you would find those is you would need to be given two values. Like you would need to be given the temperature after a given period of time. You need a couple more values. In other words, a time and a temperature, two of those. And for each one, you could solve for C1 and K. But that's where that's the general equation here for Newton's law of cooling.